Okay, what do you have for this first one up here? Why nickel 2 chloride? But why nickel 2? Why not nickel 3 or something else? Most common. So unless there's something weird going on, choose whichever oxidation state is bolded. Or if it's the only one there, choose that one. How about the next one? You mean no reaction? Not applicable? That's what you meant? Okay. Last one? Say again? This is a no reaction because this right here we okay with that? What? The last rule in the solubility rule is about sulfates, and it says they're insoluble. But any rule above that, it supersedes it. So the rule that says silver is insoluble supersedes the solubility of the sulfate, so it's not soluble. So this isn't a no reaction so much as this isn't even possible. Nothing wrong with it. It's just copper is below hydrogen on the activity series, so it will not react with it. Hydrogen is more active than copper is, so there's no reaction. What's wrong? For these guys for this single replacement reaction to happen, what would need to happen with the silver and the sulfate? They would need to let go before the iron, which wouldn't mind giving electrons to the silver before they could let go. There's no iron reaction unless the silver and sulfate let go, and they're just sitting there as a solid, so it's not going to happen.
So it's not actually aqueous.
Correct, it's not actually aqueous. True, but no. Did you look up this aqueous or the K value, KSP value for silver sulfate? I don't know what it is. It's probably pretty horrendous, like 10 to the negative 30th or something like that. Okay. What do you do first? Next. Okay, so what do we have here? I've got a +4 and a -2. I got a +6 and a -2. I've got a +3. I got a -2 and a +6. So, hate that.
Wait, I have a question.
Yes, Ty.
Is it +6 or +12? Or CR, is it like +6 times 2?
Yeah. But it's still +6. You all right with that?
Yep.
Okay. So +6 turns into +3. So this 3 electrons gained. And then what's happening here? 2 electrons lost. So what happens to the chromium? It's reduced, so then the sulfur is oxidized. Okay, what else we got? What do you want to do now? Two chromiums. So I'll change this. Hate that. I'll put a 2 right there. Now my chromiums are balanced. My sulfurs are already balanced. Now what? So I'm going to put, 2 H2Os over here. Are we okay with that? Is that right? To balance out the oxygen. So there's 2, and then there's 2, and then there's 4 over here. And then I need 7 H2Os here. Are you okay with that? Okay. Sorry, 7. Did I say 2? 7 H2Os. Now what do you want to do? Okay, what do we got? So over here I've got 14 H pluses. And down on the bottom, 4 H pluses. Okay, now what? Charges. Okay. How so? That? What? Oh, 4 H's. Oh, my bad. There we go. There are no charge on that second equation. The reactant side is neutral. Are we okay with that? The product side has a -2 and a +4, leaving you with what? What? +2. So then I put 2 electrons over there, and then that cancels out. So both sides are now electrically neutral. What do I do with the top one? Yeah, not on the right side. On the left side? On the left side, what's my total charge? 12. And what do I need it to be equal to? 6, because there's 2 + 3s on the right-hand side. Are we okay with that? Correct.
Yeah.
No. I just try to make them equal. I can't add electrons to the right-hand side and make it equal. I can only add them to the left-hand side, because the left-hand side has too many plus charges. It's got 12 plus charges, and on the right-hand side, I've got 6 plus charges. So if I put 6 electrons on this side, then the charges become neutral or even. We okay with that? Now what do we need to do? Multiply the bottom one by 3. For what reason? The electrons need to cancel out. All right, let's go to orange. So this becomes 6. This becomes 3. This becomes 3. This becomes 12. And this becomes 6. We good with that? There's 2 electrons on the right-hand side, and there are 6 electrons on the left-hand side. And the electrons need to be canceled out. So when I multiply this entire bottom one by 3, this now becomes 6 electrons. And so then I can, I don't know, how about this? 6 electrons, and the electrons are now gone. Anything else you want to do with that? Say again? Sure. I've got 6 water molecules on the left. Are we okay with that? And on the right, I've got 7. Cancel that. Cancel that. I got 1 water left. What else we got? There are 12 hydrogens here. That leaves us with 2 hydrogens over here. What's wrong? She got it? 6 of these waters on the left canceled out with 6 of the waters on the right, and that left us with 1 water on the right. And then add the equations up. So I've got 2 H pluses left. I've got a chromate or dichromate left. I've got a chromium +3, and I got a water molecule. And then I've got 3 sulfur dioxides, and I've got 3 sulfates. So what's the first thing you should check? No, not that. No. Are those okay? I've heard no 6 times and yes 3 times and still waiting. We okay with yes? So I have 2 H pluses there, right? So 2 pluses, and then I've got 1 chromate, -2, gone, right? Neutral on that side. The other side, I've got 2 + 3s giving me a +6, and I have 3 -2s giving me -6, 0. Good? What's wrong, Mary? No. Go ahead. The only reason we were looking at the individual atoms, maybe 15 minutes. All right, cool, thank you. The only reason we were separating them into individual plus charges and minus charges is because we needed to find out who was being oxidized and who was being reduced, which atoms were, okay? But now we're literally just looking at both sides of the equation and seeing what the charges are now. I'm not sure what you would do with that by separating it out, though. Yep. So that sulfate, there's 3 sulfates giving me a total of -6, right? And then 2 + 3 is giving me a total of +6, so it's a wash at 0, right? Okay. Is everything else good? The chromiums are okay, right? 2 and 2. The sulfurs? 3 and 3. The hydrogens? 2 and 2. And the oxygens? Fingers crossed. 6 and a 7. So I got 13, right? On the left and on the right. 12 and 1. 13. Okay. Nernst equation. So this could be 0 if I had written this thing poorly. What's going on with this? This is a battery, so what's happening? Somebody's losing electrons, somebody's gaining electrons. So I've got nickel and cadmium, metals and ions with each other, and those things are going to be transferring electrons based off of their concentrations and an inherent voltage, half voltage for each of those half reactions. So the first thing we do is we look up what the inherent voltage is for a standard condition, and so we're just, oh, that's terrible. I don't know why sometimes that thing at the bottom pops up and sometimes it doesn't. It's irritating. So first thing, we'll just look at the standard voltage, and then I need it'll be a voltage of cadmium and plus a voltage of nickel. So if this battery is working, what's happening? Oops. How do we know? No, you have to have it memorized. Joking. So I've got nickel and cadmium. They're right next to each other. If this battery is functioning, cadmium is on top and nickel's on the bottom. So if it's a spontaneous, a negative delta G reaction, what's happening? Cadmium metal is giving electrons to nickel ion. That's the only way the battery functions, right? In a spontaneous manner. Okay, so this is happening. Nickel is gaining electrons, and its voltage is going to be negative 0.23. Okay? Is this up here happening, the way it's written for the cadmium? It's not, correct? It's the exact opposite of what's happening. The cadmium is giving its electrons away. It's not gaining electrons. But again, these tables are all written one direction. So you have to recognize that, make that a positive for yourself, and then we can go back over here and say I've got negative 0.23 plus 0.4, 0.17, is that right? Volts? Okay. And now I need to 273, 8, 1, 318K, and so then my voltage out of my Nernst equation is going to be this 0.17 volts, and can't remember off the top of my head. Somebody have it written down. Say again? 0.00, how many zeros is it? 4? 86? 2 and 318 and 3.75 and 0.55 and 0.18 volts. I think that's right. You guys have that? 0.18 volts. Okay. All right, great. Is this a good battery? Seems kind of crappy, right? Why? It's 0.18 volts. Ugh. Any reason why it might be a decent battery? It's rechargeable. They don't mind giving away their electrons back and forth. It's easy to knock the electrons off of the nickel once the nickel has gotten them and put them back on the cadmium. Anything else? Cheap. It's fairly inexpensive. Cadmium and nickel are not expensive substances, metals. So, what's the point of the first equation? This one up here. One more thing. What's this thing here mean? Standard. Under standard conditions. So what's the Nernst equation do for you? Under different temperatures and different concentrations. So if I took the Nernst equation and made this 298 and then made these two concentrations equal to each other, what number would I get out of this? 0.17. So the Nernst equation allows you to calculate the voltage at a non-standard concentration and a non-standard temperature. So great, I've got a 0.18 volt battery and I need to get myself up to 1.5 volts. Okay, here's Ty. Are we okay with that? Everybody got that? Hand motion? This is a symbol for a battery. The long line is the positive side and the short line is the negative side. And so anion, cation. So what I would do is take this and then I would have it plug into this. And then I would have this plug into short, long, 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 short, long. We there yet? No. Short, long, short, long, short, long. So it's 0.18. Seriously? It's so close. .18? No, not that. That. Oh my God, Microsoft. Oh, need more. Looks like I need about 8 of them. Okay, and so my total voltage here at, oh, sorry, I need 9 of them. And so then I'll get, and that's a totally reasonable number. Are we okay with it being over 1.5? You wouldn't actually want your new battery to be a voltage of 1.5 because as soon as it dropped to 1.49, then the battery is kind of dead. Why